Hello, in this quick video we're going to explain the first law of thermodynamics and some specific idealized thermodynamic processes. So let's just review. We already know what the first law is. It's a restatement of the conservation of energy. And it says in equation form that delta U equals Q minus W. Why is that a restatement of the conservation of energy? Because it says the only way to change a system's internal energy, that's collective kinetic energy basically for all the particles in the system, is to add or remove heat or to add or remove work. That means have the system do work or have work done on the system. The field of thermodynamics came about really during the Industrial Revolution, trying to make sense out of how steam engines work. We know today we have the idea of the atom and molecules, but they didn't at the time. So they were trying to figure out what happened. But even though we're looking at a mechanical steam engine, literally, it's a class of things known as a heat engine, which uses an input of energy. Some of that energy is used to do work, some of it's exhausted to the environment. So if we look at a classic exploded view or a cutaway view of a steam engine, the source of energy might be a heat input, and the heat would come into the system through the combustion of coal. Some of that energy in this case would be used to drive a piston forward, and a piston is right here, so really the moving part of a locomotive is really small. So this is where the work would take place, and then of course we can't convert all of this heat into work. One of the things that we also end up doing is increasing the internal energy or the temperature of the system. Of course, all of the gases and the steam gets very hot, and it also exhausts a lot of that heat into the environment. But anyway, we can simplify a lot of processes with the first law of thermodynamics and make sense out of a lot of important things in nature. So I'm going to run through the kind of the importance of this really quickly. Here's the first law of thermodynamics, of course, up here. It's really important for us to think about 9 times out of 10 when a student comes into a beginning physics class and they say temperature measures, and you're given a choice of internal energy, heat, and work. We always go to heat. We're so convinced that heat and temperature go together, but we're actually wrong in this case. What temperature is actually measuring is the collective kinetic energy of the particles in a system, and we know that collective kinetic energy is known as the thermal energy or the internal energy in U. So that's really important for us to talk about. When something cools down or when something heats up in terms of its temperature, really what we're talking about is an increase in delta U or a decrease in delta U. Heat and work are just ways that we can change U and the temperature. But temperature measures U, not Q or not W directly. So oftentimes in nature, we make some simplifying assumptions. So as simple but profound as the first law of thermodynamics is, we can even simplify it further when we make some idealized assumptions. We could imagine a case known as an isothermal process where delta U doesn't actually change. So that would be 0. And that's the definition of isothermal. It means the temperature will not change. And delta U will be 0. The first law then would simplify to Q equals W. The meaning of this would be for any energy that's transferred into a system as heat is used to do work. So we put energy into the system's going to expand into its environment. Any work done on the system is transferred out of the environment as heat. So if we compress the system, we shed that energy into the environment as heat. So in this case, no change in temperature, no change in internal energy. You might want to review, remember we're talking about these as being idealized. What does the first law of thermodynamics, or the second law of thermodynamics say anyways, about a purely isothermal system? Is it possible to use all of my heat to do work? I'm going to leave that up for you to decide, but in any sense, the isothermal approximation, the isothermal process, is useful to us. Another idealized process in the first law of thermodynamics is referred to as an isovolumetric process. And this means, as its name implies, there's no volume change, so V equals 0. And V, of course, is volume, not velocity in this case. You got to remember, right, there's no V explicitly in the equation. Where is V hidden? V is hidden in how we talked about how a gas does work or has work done on it. Remember, work done on or by a gas is a pressure times the change in volume. So if delta V is 0, the work has to be 0 as well. So the first law in this case, an isovolumetric process, would simplify is to internal energy equals heat. This is something that we sort of come in with a conceptual knowledge already of how do we increase something's energy and make it hotter, and we add heat, right? This is the conventional sense. So any energy transferred into the system as heat increases the system's internal energy and it gets hotter. Any energy transferred out of the system as heat decreases the system's internal energy and it gets colder. So in this case, what's purely an isovolumetric process? There's not a lot of them in nature that are purely isovolumetric, but a pressure cooker up here might be an example of one. Right? In this case, we put that lid on there and it really latches on tight, and as we pump in Q in that case, what happens to the temperature inside? The temperature and the internal energy of the system inside gets larger. So there's no work done by actually expanding the walls of the pressure cooker. There is a relief valve here that if we exceed a certain pressure, we can get work out of the valve by air expanding out of it. But when it's normally operating, this is an isothermal or an isovolumetric process. Last idealized process we will talk about today has a strange word, but is super important to a lot of atmospheric sciences and meteorology, is an adiabatic process. You might have guessed we got one thing to set to 0. Adiabatic means no heat is transferred. So either we're dealing with a really well insulated system, or the transfer of heat happens, or the reaction happens so fast that there's no time for heat to be transferred. So what that means, Q is 0. And our first law then becomes delta U equals negative work. This is the one that students have to slow down typically a little bit, thinking about positive versus negative work. And this is what we're saying. If work is done on the system, remember that means that we're going to compress it, so work would be a negative value. So if I do that, I get minus a minus work. That means that these become pluses, right? And delta U increases. So the system actually has an internal energy increase, and the system would get hotter as a result. If the internal energy can be used, though, to do work, so we can use some of this internal energy, and we can cause the system to expand into the environment, to do work on the environment. In this case, expansion, remember, work is greater than 0. And we'll note a decrease in the system's internal energy, and the system will get colder. So this is something that's known as an adiabatic process. Real important to engines and also to the atmosphere itself. When air is forced upwards, it's moving to an area of lower pressure, so it expands. It does work on the air surrounding it. A meteorologist actually refers to these as parcels of air, little boxes of air. And as that parcel gets larger, it's doing work. Its internal energy then drops because of this negative sign. Its temperature drops, and if it drops to the dew point, that's where we all of a sudden get a cloud, and that's how weather starts. So how do we get this to happen in the atmosphere? Air can be forced up over a mountain, and this will happen, or a front will also do the same thing. A front will force air upwards. It'll expand, lower its internal energy, and cool to the dew point. Anyways, we're going to work with these ideas throughout the coming week. Hope this helps.